Okay, let us start. So remember, we have started with the state space methods. So when we say a state space representation, we mean this: x dot is equal to ax plus bu, and y is equal to cx plus du. In the last lecture, we have seen how we can convert a state space representation into a transfer function. And we ended up with the transfer function formula: g of s is equal to c si minus a inverse b plus d. Yeah, this is how we convert a state space representation into a transfer function. And remember, in the last lecture, we started with converting transfer functions into state space representations. And we know that that transformation is never unique. That actually means that for a single transfer function, we can find infinitely many state space representations depending on the state definition. So here, when we look at this transformation, it is transfer function into state space representation. Everything depends on our state definition. So in the last lecture, we consider a general state space form. So I have g of s is equal to b1s to the n minus 1, b2s to the n minus 2, going until bn, divided by s to the n, a1s to the n minus 1, going until an. Okay? That is the general transfer function that we would like to find a state space representation. So here, we see that the order of the numerator is always strictly smaller than the order of the denominator. When these two orders are the same, then we know that we are going to get a non-zero d, and we can make that a division, and for the rest of the transfer function, we can try to find a, b, c here. And the first important state space representation that we saw was called diagonal canonical form. And in this case, we have written this g of s. We have written this g of s in a partial fraction expansion. So in this case, we made the following assumption. So I have seen that d of s, that is the numerator here, that's my d of s and n of s. I have assumed that d of s is in the following form: s minus p1, s minus p2, going until s minus pn. I assume that there are n poles, and these poles are distinct. That was our assumption. pi is not equal to pj for any i not equal to j. Okay? This was the assumption for diagonal canonical form. This assumption is made because for some transfer functions with repeated poles, diagonal canonical form might not actually exist. So here, this assumption makes sure that the diagonal canonical form exists, and we can do the following. In this case, we can write g of s as b1s to the n minus 1 going until bn. I have s minus p1, s minus p2 going until s minus pn. I can actually expand g of s into a partial fraction expansion. Okay? And I can write this as I from 1 to n alpha I, and I have s minus pi here. And then using this partial fraction expansion, I can write what y of s is. Y of s is transfer function times the input Laplace transformation. And when I use this representation of the transfer function, then I can write y of s is I from 1 to n alpha I u of s divided by s minus pi. And now I'm ready actually to define my state variables. Remember, for each different state variable selection, we have a different state space representation. So here we select our state space variables by using their Laplace transforms. I'm assuming that the Laplace transform of the ith state variable is u of s divided by s minus pi. That is the definition of the Laplace transform of the state variable. Okay? And by using this definition, I can write y of s is equal to, instead of this ratio here, I can substitute xi. I from 1 to n, alpha I, xi. Okay? So this gives us actually an output equation, as you see. Y of y is equal to a linear combination of the state variables, where the coefficients of that linear combinations are alpha I. And now I have to find the state equations. For that, I write this equation as follows. S minus pi times xi of s is equal to u of s. And I can write this expression as s times xi of s is equal to pi times xi of s plus u of s. Okay? So now I can actually convert this equation into time domain, which is going to give me, assuming that the initial conditions of the state variables are 0, this is going to be xi dot is equal to pi times xi plus u. This is going to be my state equation, and this is true for any I from 1 to n. And now I can write these state equations and this output equation in matrix vector form. So I can write here x dot, which is the state derivative, is a matrix times x times a vector times u, and y is equal to cx, and d is going to be 0 in this case, because the numerator order is strictly smaller than the denominator order. I can actually find a state space representation with 0d for this transfer function. If d was not equal to 0, then this would have meant that the orders of the numerator and the denominator would have been the same. Okay? So here let us try to write these state equations. I see that for all states I have a similar equation, and x1 dot is going to be p1 times x1 plus u. That actually means that the first row of this matrix is going to be p1 0 and filled with zeros, and I will have a 1 here. And x2 dot is equal to p2 x2 plus u. This means that the second row is going to be 0 p2 0 going until the end, and I will have 1. I will fill in the A matrix in this form, and in which case we will see that we have a diagonal A matrix, and we have B vector filled with 1s, and finally I have the output equation, which is going to be alpha 1, alpha 2, C vector is going to be filled with alphas. Okay? So we see that in this case we have found a state space representation where the A matrix is diagonal with the poles of the system are in the main diagonal. So if you look at this A matrix, what are the eigenvalues of this A matrix? They are poles. So here eigenvalues are the diagonal elements, which are the poles of the system. That is what we have actually seen from this transfer function. Remember, instead of Si minus A in inverse, we have written adjugate of Si minus A divided by determinant of Si minus A. And this actually showed to us that in the denominator of this transfer function, I will have determinant of Si minus A, which is the characteristic polynomial of the matrix A, meaning that the poles of the system are always the eigenvalues of the matrix A. Okay? And here I see indeed that for a lower triangular, for an upper triangular, or for a diagonal matrix, eigenvalues are always the diagonal elements. The matrix does not have to be diagonal. It can be upper triangular or lower triangular. Still, the eigenvalues would be the diagonal elements. So in this case, this matrix is diagonal, and the eigenvalues are the diagonal elements, which are the poles of the system. So now we are actually ready to solve an example. Yes?
Is this form always minimal? I mean, can we find the smaller matrix in diagonal form?
In general, so when I write this transfer function, I am assuming that I don't have any cancellations. Okay? If I have a cancellation, of course, in such a case, when a state space representation is not minimal, that actually means that when you calculate the transfer function, there is a cancellation. Okay? If there is a cancellation, you can always do that cancellation first, and then you try to find this. If there is no cancellation, and if you find this state space representation, it is always going to be minimal. Okay? So I have g of s is equal to 2s plus 1 and s squared plus 3s plus 2. I know that such a transfer function is given like this. In the denominator, I have s plus 1 and s plus 2. I think you can always do such a. We have distinct poles, and that actually means that I can have a partial fraction expansion in this form. And we know that you can actually find this a and b yourself, but the result is going to be a is equal to -1 and b is equal to 3. Okay? And based on this partial fraction expansion, I can immediately define the diagonal canonical form, state space representation. So now into the diagonal elements, I will place the poles. So what are the poles here? It is -1 and -2 are the poles. And here, the b vector is always filled with ones in diagonal canonical form. And here I will write what here? -1 and 3. Okay? So that is the diagonal canonical form, state space representation for the system.
Hocam,
Yes.
here if we had a division, ya işte ilk durumda numarator'ın derecesi denominator'da büyük olsaydı işte bundan gelen sabit sayıda değil gelecek.
Yes, exactly. So let us say that instead of this, I had the following: 2s squared plus 2s plus 1 divided by I have s squared plus 3s plus 2. Okay. So here I will instead write this 8, and I will write here. Let me say 5. Okay. So let us say that I would like to find the state space representation for this quantity. Okay. So here the first thing that I'm doing is the following. I can write this transfer function as this: 2 in s squared parentheses. I have 2 in 2 parentheses. I have s squared plus I will write 3s plus 2 here. Okay. And then what am I going to add here to have the same numerator? I will have 6s here, so this is going to give me 2s, okay, plus what? Plus 1 divided by this thing, s squared plus 3s plus 2, okay? So then I see that this is nothing but 2s plus 1 divided by s squared plus 3s plus 2 plus 2 here, okay? And this actually means that I have the state space representation. ABC would remain the same. U and y is equal to -1, 3, x, and what? What am I going to write? Plus 2u. Okay. Efendim? Neler nereden geliyor? Bir şey yanlış yazmışımdır belki. So here I have used the following expression. G of s is given like this. Okay? C times si minus a inverse b plus d. When you take d0, then you would always have a transfer function in this form where the numerator has a lower degree than the denominator. If the numerator has equal degree with the denominator, then what we do is that I try to separate this thing. Okay, I separate this 2 here, and this thing becomes now d. Okay, and this thing becomes c times si minus a inverse times b. Okay, That is why, by using this type of term, I choose A, B, and C as in that transfer function, because I know that in this case D is equal to 0, and I know that the transfer function, this thing, is equal to C times Si minus A inverse times B. I know that this thing is satisfied for these ABC triple. This equality is satisfied. That actually means that I can use the same ABC here, but I can add a D term with a non-zero D to complete the state space representation. So now this was the first state space representation that we are going to see. The second one, and the second and the third one will be much more common, okay? And they're going to be called controllable canonical form and observable canonical form. The first thing that we will see is controllable canonical form. In controllable canonical form, we are going to use the same representation here. I'm going to assume the same general form, and I will do the following. G of S is, instead of this denominator, I will keep it as D of S. Okay, B1 S to the n minus 1 going until Bn divided by D of S, and I will write this thing as follows: B1 times S to the n minus 1 divided by D of S plus B2 times S to the n minus 2 divided by D of S. These are going to continue in this manner. So I will continue until Bn minus 1 S divided by D of S plus Bn, I have 1 over D of S. Okay? So here, let us write the output. Y of S is equal to G of S times U of S. G of S times U of S. So I will just multiply this thing with U of S, and that is going to give me Y of S. Okay? So Y of S is equal to B1 times S to the n minus 1 U of S divided by D of S plus B2 S to the n minus 2 U of S divided by D of S. These would continue in a similar manner. Plus, so I will continue Bn minus 1 S U of S over D of S. All of these struggles are for being able to define our new state variables. The question is, what are we going to define our state variables? We are doing these type of manipulations just to see what our new state variables might be. Plus Bn U of S over D of S. And now in controllable canonical form, we are going to be defining our state variables from these quantities. Okay? So these are going to be our new state variables. So I will define for x1 of s is equal to u of s divided by d of s here. Okay? And x2 will be s times u of s divided by d of s. I clearly see that s times x1 is actually x2. Okay? So this is nothing but s times x1. Okay? I will continue in this manner until let me say xn minus 1. This is going to be s to the n minus 2 u of s divided by d of s is equal to, so that is the definition of xn minus 1, and this is s to the n minus 2 times x1. And finally I will define what xn is. Xn is s to the n minus 1 u of s divided by d of s. Okay, it is just this final one. Okay, that is s to the n minus 1 times x1. All right. So now we can actually try to look at what our state equations are. Remember, in a state variable, in a state space representation, what we are doing is that we are expressing the derivatives of the state variables in terms of the state variables and the inputs. So here, derivative of the first state variable will have the following Laplace transform, s times x1. I'm assuming zero initial conditions here. S times x1, I need to write this as a linear combination of the state variables and input. What am I going to write on the right hand side? This is going to be just x2. S times x1 is equal to x2. Okay? And I have s times x2 it is just going to be x3 here. So I will continue in this manner, and I will write s times xn minus 1 is equal to, it is just going to be xn here. S times this thing is going to give me xn. Okay? And then the question becomes now, what is going to be the s times xn? What is this thing? These are all state equations. I can write here x1 dot is equal to x2. x2, instead of this equation in time domain, I can write x2 dot is equal to x3, going until xn minus 1 dot is equal to xn. Then the question is, what am I going to write for the last state variable? In order to be able to write that, I will use this last equation. Oh, sorry, the first equation that I have written there. I haven't still used the definition of d of s from that equation. So I will use that to calculate what s to the xn is in terms of the state variables and the inputs. So x1 is equal to u of s divided by s to the n plus a1 s to the n minus 1, going until a to the n minus 1 s plus a1 an. Okay? I have this equation. Now I can distribute this equation to write the following: s to the n x1 plus a1 s to the n minus 1 x1, okay, going until a n minus 1 s x1, and I have plus a n x1 is equal to u of s. Okay. Now I can actually try to replace some of these variables in terms of the state variables. So what do you think s to the n x1 is? I need to write it. S to the n minus 1 x1 is xn. Okay? So if I separate one of the s's from here, this is going to be s times xn, which is what I'm looking for. Okay? So this is s times xn. Okay? And then I will take these terms to the right one by one. I have here minus an x1. Okay? I will take this term to the right. What is s times x1? It is x2. It is an minus 1 x2. Okay? These are going to continue until this term minus a1. What is this? S to the n minus 1 x1. What is that in terms of the state variables? It is s to the n minus 1 x1. It is just xn, okay? And I have here plus here. Now I can convert this equation into a state equation. And how can I convert it? So this thing is xn dot is equal to, it is minus an x1 minus an minus 1 x2 going until minus a1 xn plus u. That is my last state equation. Okay? So I have xn dot is equal to minus an x1 minus an minus 1 x2 going until minus a1 xn plus u. And let us also finally write the output equation. The output is given as b1 times, I have, this is xn, plus b2 times xn minus 1, going until bn times x1. That is going to be my output equation. Y is equal to b1 xn plus b2 xn minus 1, going until I have bn minus 1 x2 plus bn x1. Okay. So now let us try to write this state space representation. I have x here. I will have a square matrix. I have x and b here and u, and y is equal to c times x. Let us first write what c is. C is going to be written from this equation. What is going to be the first coefficient? Coefficient of x1 is going to be in y. What? What is this? bn. So I will go in reverse order here, bn minus 1, going until b1 here. Okay? So I will write what was the transfer function here. G of s is b1 s to the n minus 1 going until bn divided by s to the n, a1 s to the n minus 1 going until an here. So in controllable canonical form, I write the numerator coefficients, numerator polynomial coefficients in reverse order into my C vector. Okay? So now let us try to write the A matrix. In A matrix, I'm going to use these state equations here. x1 dot is equal to x2. That means that the first row should be what? 0, 1, and I will have all zeros here. The second row is going to be x2 dot is equal to x3, meaning that the second row is just going to be this. And these are going to continue until the end actually, okay? So I will have all zeros here for the first n minus first equations. I'm going to write something like this, and I will have zeros everywhere else on the diagonal, and I will have zeros here. So we see that on the main diagonal I will have zeros except for the last row. And in the first super diagonal, this is super diagonal and this is sub diagonal. This is the first super diagonal. I will have all ones, and then I will have the rest is going to be equal to 0 in the first n minus first rows. And in the first n minus first equations there are no inputs, so the input terms would all be equal to 0 for the first n minus 1 elements. And then let us write the last equation. The last equation is going to be the coefficient of x1 on the right hand side is minus an, and then I have minus an minus 1, going until minus a2 and minus a1 here. And what is the coefficient in the last equation of the input?
Wow.
It is just 1. So we see that in controllable canonical form, the A matrix is feel like this. B matrix, B vector is all 0 except for the last element, which is 1. And the C vector is composed of the numerator coefficients in reverse order.
Okay.
Yes.
Where does the name controllable come from?
Yes, that's a good question. I will not be able to explain it until next week. In state space systems, we can apply a very strong control mechanism that is called state feedback. So far in this course, you have only seen something called output feedback. So when we have G of S, then we saw how to feed the output only back to the input side. Okay, so this was our controller GC of S. We saw how to feed the output back to the input side of the system so far in this course. In the last week of this course, we are going to see the following. We are going to have the state space representation of the system. Okay, and this is the output Y, and this is the input U. What we are going to do is a very strong control architecture that is called state feedback. Instead of feeding the output only back, we are going to feed the state of the system back to the input side. Okay? This is going to be a vector now, so I need to convert it into a scalar. I will multiply it with a horizontal vector, and that is going to give me a scalar. Okay? And then I will feed the whole state back into the input side. That is going to be called state feedback. And when we apply state feedback, we are going to see that if the system actually satisfies some important criterion, if the state space representation has some important property, then we will see that we can place the closed loop poles of the system using state feedback anywhere we like in the complex plane. Okay? It is really going to be a powerful control mechanism. By choosing this K, we will be able to place the closed loop poles anywhere we like. We will not be constrained by the root locus or anything like that anymore. We can choose arbitrary locations in the complex plane, and we will be able to place the closed loop poles anywhere we like by choosing this K, if the system has some important property. That property is called controllability. Okay? That is going to be the next topic after we see these representations first. That is why this representation is called controllable canonical form. When we look at this state space representation, when we see the conditions for controllability for a state space representation, we will see that such a state space representation would always be controllable. Okay, that is why this representation is called controllable canonical form. So here let us look at some examples. I need to find state space representation given in controllable canonical form. Okay? So here I will write x dot is equal to, what is going to be the size of my A matrix? Size of A matrix, 3 by 3? It's going to be 2 by 2. The order of the system is 2 here. That means that, so here there are n elements, the order of the system is n. So I have here 2 by 2 matrix and 2 by 1 vector, and y is equal to cx here. Okay? So now what I'm going to do is that let us first fill in the A matrix, which is, the B vector is the easiest. It's going to be filled with zeros except for the last element, which is 1. So I will have B vector is always in this form for controllable canonical form state space representation. And B vector is going to be, I will start from B1, which is 2 here, and then it is 1, and B vector will be written like this. And A matrix is going to be filled with zeros except for its super diagonal, which is going to be 1, and except for in its last row. The last row is going to be filled with A coefficients. This is A1 and this is A2, and I will write them in reverse order here. Minus A1, so what is going to be this coefficient? This is going to be minus A1. What is going to be this? It's minus 3, and I have minus 2 here. Okay? And the main diagonal is 0 except for the last row, and super diagonal is 1, and that completes the state space representation. Okay? Now we have a tricky one. It is 5 s cubed plus 10s squared plus 2s plus 3. In this case, what is going to be the size of the A matrix? It's 3 by 3. So I have x dot is equal to, I have 3 by 3 matrix, 3 by 1 B vector, and y is equal to c times x. So now the B vector is the easiest. It's filled with zeros except for a 1 at the end. And C vector is going to be composed of the numerator coefficients. That is the trickiest one. Let us first fill in the A matrix. Okay? So in this case, I need to write here the last row. Let us write it first. Minus A1 is going to be minus 10, minus 2, and minus 3. 3 here. I have written these coefficients in reverse order by multiplying them with -1. And the main diagonal is 0 except for the last row. And finally the super diagonal is 1, okay? And the rest is 0 in the first two lines. And finally I have come to the C vector here. In C vector I have to write the numerator coefficients, okay? If you do this, then it's not going to work. Is this correct? I have to write this thing as follows. So in this general form, we see that the coefficient starts from the order 1 less than the order of the system. Okay? So this numerator is actually 0 times s squared plus 0 times s plus 5. Okay? So you have to consider this one as B1, B2, and B3 here. We see that B3 should come at the beginning of this vector. Okay? So what should be this vector now? It should be B coefficients in reverse order. 0, 0, 5. Okay? Yes. Efendim? Because here we have found this representation for such a transfer function. Okay? And such a transfer function, if it has s to the n here, the coefficients in the numerator increases their power until n-1. Okay? That is why here, because of this s cube, I have something starting with s squared. So now let us try to concentrate on this formula. G of s is equal to C Si minus A inverse B plus D. This is our general formula for transfer function state space representation relationship. So in the controllable canonical form case, we have found G of s is equal to C times C controllable canonical form, Si minus A controllable canonical form inverse, B controllable canonical form here, okay? And plus D controllable canonical form, okay? In general, I don't have to consider D here, but we can always find D by division if the orders are equal for the transfer function. So now I have this transfer function. So this thing is a scalar, okay? And the right-hand side is a scalar. So when I take the transpose of both sides, what happens to the equation? It's going to remain the same. It won't change because we have a scalar here. So when I take the transpose of G of s, it's going to be itself. Okay? So that is G of s. D is a scalar, so when I take its transpose, it's going to remain as itself. Okay? But these are vectors. So if I take the transpose of a matrix multiplication, how can I write this transpose? This is going to be B transpose and A transpose. The order is going to change. Okay? So when I take the transpose of this thing, I will take the transpose of this thing first and I will write it here. B controllable canonical form transpose. Okay? And then I will take the transpose of this thing. Transpose and inverse can be interchanged always. Okay? And the transpose of an identity matrix is itself. So I will write here Si minus A transpose controllable canonical form, okay, inverse, and I will take the transpose of this thing, C controllable canonical form transpose, okay. So now I have obtained a new formula for the same G of s, okay. Now what we do here is that I can actually consider this, I can compare this to the general form, okay. So here, the transpose of B controllable canonical form can act like a C vector, okay? And the transpose of C controllable canonical form there can act like a new B vector, okay? And A transpose can act like an A matrix, okay? So we call such a representation when A is selected as A controllable canonical form transpose, when B is selected as C controllable canonical form transpose, and when C is selected as B controllable canonical form transpose, we call such a representation as observable canonical form representation. Okay? That is observable canonical form representation. And D remains the same. D, observable canonical form, is equal to D, controllable canonical form. Okay? So now if I would like to write such a representation, then it's going to be looking like the following. So I have this U, and Y is equal to Cx. Let us try to write observable canonical form representation for such a transfer function. Okay? I know that here, this C observable canonical form is going to be the transpose of B of the controllable canonical form. I will write the transpose of this thing as my C. It's going to be 1, and I will have zeros everywhere else. Transpose of that vector is that. And as B, I will write the transpose of C here. Okay? It is going to be B1, B2, going until Bn. And finally, I will take the transpose of the A matrix. In the A matrix of controllable canonical form, the last row was filled with A coefficients. In its transpose, where should I fill with A coefficients? In the transpose, it's going to be last column. Okay? Minus A1, minus A2, going until minus AN. Okay? And the rest is 0 except for the super diagonal. When I take the transpose of this matrix, everything is going to be 0 except for the subdiagonal. Okay? So here, the diagonal is still 0, and the subdiagonal is filled with 1s in its transpose. And I will have zeros everywhere else. Let us now do the same thing to these examples. I will now find the observable canonical form state space representations for the same transfer functions. In this case, C is quite easy. C is filled with zeros except for its last element. And B's are filled in reverse order into the B vector now. So I have 2, 1 here. Okay? And the A matrix is filled with -3, -2 in its last column. And subdiagonal is 1 and diagonal is 0. And finally, I have in this example a 3x3 observable canonical form representation. In this case, C is quite easy. And B is filled with, tell me what B should be. Yes? Yes, it is going to be 5, 0, 0. B1 coefficient is 0, 0, and 5. And finally, I have -10, -2, -3. Diagonal is 0, subdiagonal is 1, and I will have zeros everything else. I have defined something called observable canonical form. What is that?
Y equals sum of states vector.
Yeah, but there is also another property of a state space representation, which is called observability. So in general, in state feedback, what we would like to do is the following. This is my state space representation. Y is equal to Cx. We extract the state and we feed it back into the system side. And I have a K here. And I close a loop given like this. This is U. This is Y. That is state feedback architecture. And we are going to see that this is really powerful. We will really like to do this. But here, for making state feedback, I need to observe the states. I need to measure them for feeding them back into the output side. In general, in systems, only the input and the outputs are measured. That is why, when we cannot measure the state, sometimes we would like to do still a state feedback. And the way to do that is going to be the following. I can actually define a computer algorithm, an algorithm somehow, that is called observer. Okay? This observer can estimate the state of the system. It is not the actual state, but can estimate of it. Okay? And then I can apply state feedback by using the estimated state. Observer concept is an important concept in control, and it is what my research is actually based on. That is probably why we will not be able to have time to teach that topic in this semester. Observer hiçbir zaman zamanımız kalmıyor. Geçen sene de kalmamıştı. Bu sene de muhtemelen kalmayacak maalesef. Ama observer tasarlayabilmek için sistemin bir property'si olması gerekiyor. Ona da observability diyoruz aslında. Bu dönem derste gelebileceğimiz en son nokta observability kavramı. Observability kavramını kullandıktan sonra maalesef observer design'ını anlatamayacağız zaman eksikliği sebebiyle. Geçen sene şöyle bir şey olmuştu. İşte son sınıfa geçen arkadaşlarınızdan bir kısmı Kalman filtre nedir filan diye merak etmişlerdi. Onlar benimle böyle 1 saat 2 saatlik bir zaman ayarlamıştık. İşte 20-30 son sınıf öğrencisi gelip onlara hem observer anlatmıştım hem de Kalman filtreyi filan anlatmıştım. İstediğiniz zaman öyle bir şey yapabiliriz gene arzu ederseniz. Biraz geçirdim, kusura bakmayın. İyi akşamlar. 12 diye biliyorum ben. 12. Evet.